Today we're going to talk about exploiting rich content. As you can see here, I'm just playing the slide deck here. More or less, the purpose of talking about this is that remediate technologies, rich internet applications, are being deployed massively across all kinds of applications, consumers everywhere. And I think one of the main reasons about attacking remediate technologies is all about the massive deployment, right? Back 10 years ago, it was all server technologies. We all audited. First it was Unix for a while. Those got kind of patched up a little bit. Then we went to Windows and audited those. And then the FBI top 20, if you follow those, migrated over to consumer technologies as cable networks, digital, and DSL subscriber networks started patching these and firewalling these filters off. The focus went on client technology. So now the major threat to a lot of us, of course, are client technologies. So I've repositioned myself in looking at client technologies. So I more or less want to go out there and look at these technologies and figure out what kind of real threat that they present to us as security researchers and engineers and developers and CISOs and all you guys there, and also as consumers, and really get an idea of what's there. So initially I went out, looked at all these applications, things like Java, Flash, Silverlight, and get an idea of really what I want to kind of go after and look at and analyze. And through that research, I found that Adobe Flash is by far the highest deployed technology. It's everywhere. Linux, Unix, Macintosh, you name it. Windows, all over the place. So the course of this presentation I'm going to present today and talk to you guys, we'll cover 3 main categories. Adobe Flash introduction, where I'll talk about the Flash technology. Most people in this audience, I assume, already know a lot about Flash. Everybody uses it. But I'm going to talk more about the centrics and deeper technology to give you an understanding. And then I'm going to go on to my test methodology, about how I audit the technology to find vulnerabilities and find security holes, and then, of course, the results of my audit. So first things first, deployment. So the Miller-Brown survey was a survey that was conducted across the US and over in Asia based on browser usage and how many people actually had Flash installed. This is across all platforms, Linux, Unix, Windows, Macintosh, OS X, obviously. And based on that, as you guys can see, 99% of the systems had Flash. What that means is that any critical risks in Flash could potentially affect, according to the survey, which always results, they're stats. Statistics are always based off a sample group. That's not the whole world, but it's fairly reliable input here. But these issues can affect 99% of people out there that are internet using PCs, or of course Macintosh systems as well. Yeah, for that reason alone, that kind of base makes it a high target, a high value target. Shockwave Flash delivered through the .swf file format. And then that file format itself is, imagine like you have like an ELF binary or a P or something else. It's more or less an executable file format. You have code, you have data sections, you have string tables. It's a rich package shipped across the wire to someone else, fully functioning. And Flash content, and one of the reasons that it chose Flash is Flash offers a wide variety of functionality. By far, it's one of the most popular technologies out there because of its rich functionality. People using it in entertainment, for online gaming, for media streaming, for video. So for obvious reasons, that's kind of the focus of my technology, or the focus of my audit here that I've done. Also, furthermore, Flex and Air are 2 additions to Flash that add modular libraries, things along those lines, to make it even more diverse and richer in content in that sense. To make it a technology that's even more usable and more seekable by developers. The file format is typically 64 tags as of Flash version 9. Of course, this is always increasing with future versions of Flash. There have been several versions of Flash, and obviously we're now in version 10. The most usable versions now are 8, 9, and 10. 9 is out there all over the place. 10 is being used more because it offers much richer functionality. Flex and Air use 10 and 9. So the more that the Flash you download to your browser, it's going to be 9 or 10. Tags are TLV. Those of you looking at network protocols, type link value kind of structures, the way it's organized to describe the length and to be able to parse through that stream. And many of the tags support subtags, which support subtags. It's actually a very complex file format. Looking at it, there's a hierarchy that goes. It's painfully deep for those of you that have had to reverse engineer decompile Flash. There's 3 core things about Flash you have to understand if you're looking at Flash technologies. The stage is one. The stage is where your movie is painted to the screen, where you do animations and in your frames. It's kind of the area. Obviously, a movie like theater, they call it the stage. The timeline is the area where you organize your frames sequentially in a linear fashion. And you edit those frames, and you paint them on the screen. And there's assets. The concept of assets is like audio, video, pictures, anything you import or you put onto the stage. And each stage you have your timeline. Action script. So one of the initial advancements by Macromedia that was done to Flash, obviously, is they want more control over the movie files. Besides just having like this linear movie of frames and pictures and audio, to be able to control that and have user input involved. So ActionScript was introduced. ActionScript 1.0. Initially, Flash was acquired by Adobe in 2005. But it was, as I show here, it was initially designed for simple animation, but it's extended for much more. It's a rich programming language now. It's based on ECMAScript. Those of you that have, probably everyone here has seen JavaScript and work with basic scripting languages, obviously. It looks very similar to that, but it has its own libraries and includes like any other programming language. So it's much richer than just basic JavaScript. Whenever you compile ActionScript into your code, it's compiled into something like an intermediate language, like an IL, where there's bytecodes. It's a sequence of those as well. As you can see here, I've done a little pretty image here, showing the linear nature of these structures. So whenever you compile ActionScript, each operation, like an add or kind of like assembly language for those of you here that have ever worked with that, which probably about 5%, but that's fine. Now, those of you that have ever worked with it, you have basic operations like add, plus, call, those kind of things, like basic operations in the language, are reduced down to one action record for each operation. Okay? And those exist inside the parent tag of doAction. So doAction is for ActionScript 2. Okay? Just like any file format, like I talked about L for P or something else, this is your code section where your code exists. Okay? Now for ActionScript 3, you have doABC, ActionScript bytecodes, but it's more or less, it's very similar, but the structure is different. The same functionality, a little bit richer in ActionScript 3. And whenever you terminate the end of the tag, the end of your stream of records, your instructions, is followed by what's called an action end instruction, which actually it's just a null, 0, 0. That's the bytecode for that. Here's a sample for ActionScript by get URL. It's a simple function call you can just call. Obviously, self-explanatory. It will call URL. Just go to it'll just go to that URL, bring the content back to you, present the UI. That's presented when it's compiled from like Flash Professional or like CS4, like one of the popular Adobe tools. You'll see this. This is more or less the file format, more or less tag by tag. You have your doAction, like I spoke of before, and then action get URL. Action get URL has an argument built into the tag for a string, which is the URL you provided. So pre-built in. Very simple. A little bit more complex, to create text field. So the languages like C#, C++, all these things, we work with UIs, and you have a text box, and you assign data to that text box. So it's a similar kind of programmatic, where you're assigning text to that text box here. So here you create a text field that's painted on the stage, or painted like when it renders in the browser, painted on the screen, and you can assign text to it. Like TF is the the first argument here, as you can see, that's the name of my text box, or my text field rather. And then the member variable .text is where I'm going to assign the data to that text box and paint it on the screen. So the result of that is here. Hello world. Simple enough. So we're going to briefly walk through the structure of all these action records to give you guys an idea of how the action records, the bytecodes work before I move on further in my presentation and talk about some of the advanced topics. And as I mentioned before, the L file format, PL, these things, they have string tables. The concept, whenever you compile a language, is you have a set of strings. You have to be able to reference those later. So you have a thing like what's called a string table. It's used in most compiled languages and compiled file formats. And that table will be referenced later. So here we have it's called a constant pool, constant strings, as in const, char. You guys remember that from C declarations kind of thing, some kind of thing. It's a declaration of strings that are defined and stored for later reference. Each one is given an ID. Here you can see constant 0, 1, 2, 3. Later on, throughout the action script, you reference these. You can call upon them, pass them as arguments, whatever else, as we'll talk about more later. Action push. Push just an assembly, like an Intel assembly or any other machine code language. You're pushing arguments onto the stack so you can later on call them off and pass them on to further functionality. You have same thing, you have 16-bit, 32-bit, 8-bit instructions here. So here what we're doing is we're pushing a series of arguments, and we're passing that down to call function. Whenever you do an action call, you pass the arguments, the amount of the arguments to tell the handling code, how many arguments to pop off, what kind of arguments they are, and where to pass them to. And in this case, we're going to call that create text field function I showed before in the source code. So for every function in ActionScript, you have a handler that handles those arguments, and that handles that coming in, that pop them off the stack. So we have a call function. Call function, simple code here, 88. All this is call. Pop the result off the stack. Get variable. In this case, we're going to get that variable we just created called TF. We're going to acquire that, get a context to it, or get a reference to it. Now we're going to push more information on the stack. We're doing an assignment. This is what's coming up. We're going to assign hello world to TF. That's done to the set. The set member function here. So now we've assigned that text to the member variable of TF. Fairly simplistic. So a summary of this, constants are defined in string tables, key value. Well, I'm going to talk about this more later through exploits and kind of further the research. Obviously, they're later referenced by their ID, as I showed before, the 0, 1, 2, 3. You can reference those. It's like push 0, push 1, push 2, same kind of thing. But you have to define as a constant, so you have a structure. Push 0, the type of your push, the type of data structure, and then the value. And in ActionScript 2, this is accomplished through action records and do action tag. As I mentioned before as well, is that through ActionScript 3, it's do ABC and those functions. It's still a bit different. So testing. So going on, this is a series of, I used to do this throughout all my testing in my career, 3 phases. The first is manual. I did surveying, analyzing technology, getting a feel for it, then doing reverse engineering to get deep inside the technology and analyze what people don't want you to know, and really get in the seams and get a feel for the architecture. And then fault injection. To finalize all that research, you build into an automated testing technology. And we'll talk about this more in depth over the course of this presentation. Manual testing. So one of the first things, it's a great aid. One of the iSEC employees, Josh Alonis, developed a template for the binary editor, which, if you ever analyze file formats for malware or structures, it's a fantastic tool. I've got a little snapshot here. And you see in the far right column, there's the actual stream, the printable stream. You have the hex in the top column. And below, and the bottom table there, shows the file format broken down. And that's accomplished through what's called a template. You should create a template for the file format that breaks it down so you can see it, you can analyze it, and you can look in depth in that. The binary editor, they call it the binary editor. The name is the 010 editor, obviously, but the binary editor. It's formats for like GIF, JPEG, every major file format. So it's fantastic. All the guys on antivirus use this. If you guys haven't used it, I highly recommend it. The template for Swift was Josh Alonis published this to Sweetscape, the vendor for the binary editor. Now it's available to everybody here if you guys want to grab it. If you're looking at flash malware, it's a fantastic tool. Here we have a snapshot going a little bit deeper. And then, as I described before, the tag format, you can see the do action tag, get URL, and highlighted in blue there in the middle. There's the URL. It's that string table. So you can dissect these and look at them and figure out what's going on, which is great for looking for flash malware. And this has been available for about 2 months, I believe now. So I highly recommend, if you guys, those of you that are out there in high tech, they're looking at what 2.0 flash technologies, doing malware analysis, this is a great solution. And of course, writing flash movies. I can now develop flash movies, which is something I thought I would never ever do. That was, we would do a prerequisites for this talk. It was reverse engineering, Intel assembly, bytecodes, C, C++, and writing flash movies. But that combination was pretty rare, we found. So, now I can write flash movies. And now, I was highly impressed that the Flash UI for development is it's easy to use. And we'll talk about it here. There's a toolbar on the left here. It's kind of like Photoshop. Those of you that have done imagery work in Photoshop, very similar. But imagine like Photoshop, but you can add ActionScript and code and give your images context and make the movies. It's very similar. If you go ahead, I think it's F9 or F7, you bring up the ActionScript window, which I've presented here in the middle. And you look at the bottom there. You can add script code and give your movies context and motion and do which one. You can add forms and that kind of thing to make an actual program. The stage, as I talked about before, where you can present the movie, is kind of behind this ActionScript window. So where you paint it on the screen, you can look at it and analyze it. The next phase is reverse engineering. So this, I think, should always be a key phase. When you go after a technology and you want to audit this technology and understand it, you have to get in and get in deep and look at what's going on and analyze it. Basic white box testing only solves so many problems. Reverse engineering will give you an inside look at what's really going on, like what kind of attack classes and bug classes are there, what the vendors typically don't want to tell you about. And so doing reverse engineering, analyzing it, going looking for vulnerabilities. So we found some issues there, but more or less you get real insight on how to further your testing. For example, I have a bullet point for security policy, which in the world of Web 2.0 is the same origin, all these policies. You really want to know how these are enforced. What technologies, what functionality is put in place to apply these restrictions and these restraints to restrict access between different usages. So the final phase was to develop a fault injection solution. Fault injection, fuzz testing, yada yada, different names for different technologies. So flash fire. Fire was a kit that I created while iSEC partners. Fault injection for reverse engineers. The way I looked at fault injection technologies is that typically you create them to find problems in code, but you kind of randomly throw data at an application and hope it breaks. But the difference is, I think, with fire is that as a reverse engineer, you go in and you analyze technology and you find things in the application you can utilize to better enable your fuzz testing or your fault injection to make it faster, more efficient, and more successful in accomplishing your goal. This is accomplished in a series of phases here, as we'll talk about in depth. Gather input. First off, we wrote a section using the Google SOAP API. Those of you who have used that, you can acquire, you can do searches automated through Google for file formats. So I download 5 gigabytes of Swift movies. And then based on those, you analyze them, categorize them, place them where you need to be, and kind of find what you're looking for. They're sorted by unique MD5 hashes. Then surveying. So surveying the input to find out, you want to find the data that you want to use for your testing, for your fault testing, and store that. Things that can, for my example, obviously I've talked about ActionScript 2, so I want to find Swift movies that have ActionScript 2. So I find those and I categorize those to find as much content as I can and categorize it. So, to mention this, so there's different ways of doing fault injection. You have mutation and generation. As some of you know, so mutation is taking known input, for example, my Flash movies, and augmenting that to change fields and integers to create conditions later on when I pass off the application. There's also generation. Generation is great for application protocols or ASCII protocols, where it's simple to create the input and fire it off to your remote channel, to your remote target application. And in this case, obviously, I can't sit and generate remote Flash movies. The content is so in-depth and so rich, it's more practical for me to mutate existing input to find issues. The final phase, so I think one of the advents that I do is process instrumentation. That really, I think, makes a difference in fault injection and fuzz testing. And that's to hook into the target application, to hook into key points, and then analyze for events. Things like stack cookies get corrupted. For example, in Windows, which is my target platform, there's a GS cookies. I'm able to hook functions in there to detect. If a cookie is corrupted and the application exits, I can detect that. Because when it's automated, it's running day and night. You have to catch all these events. Otherwise, you may miss serious issues. You can also hook heap cookie checks or coalescing in the heap, which is when you merge blocks together. You can catch those. Or for example, failure conditions. Whenever Flash generates an error, I can catch it. So I plant basically breakpoint instructions across the application. And then I monitor those instruction addresses for whenever events are delivered to me. I can correlate them for my testing. So, process monitoring. So this kind of goes back to what I was previously talking about. So one of the great things about doing this process instrumentation allows me to do some things. For example, imagine a linear path from start to end in your applications. Well, the input is passed in, and then once it's processed, it's the endpoint. I can mark the end, the beginning and the end, and all the points along that track. And I can track how the data is being traveled. If it breaks off of its seam, I can detect that. It hits endpoint. So typical fuzz testing is all you guys have written, or fault injection. It's based on timing. You give it 100 milliseconds, half a second, 5 seconds for each delivery of your fault or your fuzz test. For this, there's no timing. It's as fast as the hardware works. So it makes it very, very evil, which I'll talk about later, how fast it'll work. Evil in okay way. Not a bad thing here. So event-driven fault injection. So what is this I've been talking about? As I mentioned, it's tight coupling between these events and the target tester. I think it's real way to acquire testing technology, especially when you're doing black box testing, is you have to get your application, your tool you're developing, to couple as tight as possible with your target application, to get as much out as possible, which requires reverse engineering, as I mentioned. That's why we call it fault injection for reverse engineers. You can't just randomly fire data at this application. You have to know what's going on inside. The pros, as we talked about, the distance traveled by mutated data in the application, we can measure that now from start to end. We can measure when it enters the application and when it exits. Allows us to detect things like, for example, let's say I'm testing Flash and it times out. It's a script running too long. I can detect that because it never hit the endpoint, and I can just kill it off. Or if a failure is detected, like, hey, action script's not valid, I can cancel it off. It's not a big deal. I think one of the most important things about this, besides the speed is definitely a huge pro here. One of the most important things is I can tightly correlate every single input that I deliver to the failure that's being created, taking these faults. So for example, I have over at 5 bytes of the heat, and normally through fuzz testing, that'll happen 100 iterations later when the application fails. I can correlate that and detect that at that moment, and then log that sample input, record it, and create a report. Right, so we're testing for a vendor or some of our clients at iSEC partners. We can create a technology. We've used this technology. We can create it and deliver a finalized report that's readable, it's usable by people. That's not just me coming in hey, you have a bug here, you have a bug here. To correlate these events. And of course, the speed, which we'll show later. The cons, of course, it requires reverse engineering. But this is black box technologies. If you're looking at something, you have to reverse engineer and mark these addresses and mark them with breakpoints and all these things. You hand code them into the, I have a configuration file, you supply the breakpoints into that, and you code them in. But if you have source, it's a whole different thing. If you have debug symbols, you have a function name. The second thing here, the last thing rather, post-mortem analysis. So whenever these faults are found, like we find stack overflows, heap overflows, integer overflows, all these things, is to analyze the context of the CPU registers and the stack to determine the kind of issue and also to determine the severity of that issue as well. And there's only so much you can do here without getting overly complicated, but you can do simple tests like repeating patterns on the EIP or the registers. Is a register 0, possibly a null pointer? Is the call stack mapping to reachable code? No, quite possibly Stack Overflow. Otherwise, or corruption. There's a lot of logical decisions you can make based on this. So we do this in post-mortem analysis. So when the bugs are found, they're categorized, given a severity. So thousands of issues you find that are all like null pointers, all these things you can ignore. You can focus on the more important ones, the P1s, the P2s, the P3s, the things that are higher in your development that you want to correct and fix. So demonstration time, I guess. Forgot about that slide. So this has the UI. So the great thing is the speed about this. I think typical injection, you have 100 milliseconds. We're at 200 injections there, and that's more time. And now, my test that I'm performing here is on an unpatched Flash player. I'll also kind of describe that too. As well, the Flash player that I audited was from last year. We contacted Adobe, and working with them, these guys responded very quickly, patched these issues. And so this is horribly broken, but this is an old version. So what you're seeing here is identifying different issues in Flash through integer overflow fault injection. Now we're at 6,000 faults. So the main thing I guess I took from the exercise was the speed. Because of the synchronization of the events, instead of waiting for there should be the testing, kind of fire away an application and hope it breaks, and then go back through and look at the log files and try to figure out what caused it. You know exactly what caused it and when, and you're 10 times faster by instrumenting the application. And you can do it for most server protocols as well. You just do it locally through loopback, and you hook the target process with a debugger, whatever you're using, whether it's Linux or Microsoft debugging API or summary. So in my testing, 3 million injections in a little bit over a day and a half. Out of that, the 23 unique vulnerabilities found in the Flash player. And out of those, 785 paths to those issues. For example, say I find one function that's a string copy, but I found 45 uses of that function. Doesn't mean it's 45 security holes. That means there's one bug in this one function. It's a helper function that's all over the place. So those were condensed down through post-mortem analysis, as I described earlier, to 23 unique paths. So what it pounds out to, so something very interesting to take away from this is you have a couple of heap overflows, you have some uninitialized data, you have null pointers, but most importantly, it's these read beyond bounds. And to look at this, it's not just because it's a Flash player, it's because of unmanaged code, C, C++. I think this will affect any vendor out there. And then now we're going to go into the, so the phase of this is, those of you in the audience have looked at heap overflows, stack overflows, and I'm not going to talk about it. It's so rehashed. There's a book called Buffer Overflows now. I won't even go into that. We're talking about some new stuff. We're going to talk about the read beyond bounds. Issues that, so I think this issue is prevalent in modern software. It can be used in a way that I think that people don't really expect. So for example, I have a sample code here. And this simple sample of C, all this does is read memory into URL. And it's checked. It's allocated for a block link. But this presents somewhat of an issue. The current way of thinking, the way that we think about software, when we're looking at software, especially those of you that are auditors, we look for things like buffer overflows and these things where we're corrupting information. But in the reality, there's more to this. There's not just where we're copying it to, where we're copying it from that's changing. The more that we're moving to these thin, thick clients, we're using browser applications for all of our work on a daily basis. They have all our financial security. There's data in our browsers that's sensitive. So if we can copy that, if we can get access to that, that's bad news, obviously. That's more important than getting EIP, or getting execution. Because the end goal of that is to get on the machine and get this information. If you can just get it, then these guys are good to go. We're trying to stop. So for this sample I provided, there's a mem copy that's provided down here. Imagine that length is being provided from a structure. It's being provided from a file format. Okay? This file is being copied into memory. And we have a length at a dynamic stream. What I mean dynamic is the size is described by that length. And this size says, hey, no, there's 2 kilobytes. But in reality, it's 5 bytes. And it's the end of the file. Now it's going to be on the end of that stream into heap memory, potentially copy out sensitive information from the heap into that block, which we'll talk about more in a second. So the issue of read beyond bounds, this is an issue that I've gone back to some research looking at like terminal services, for example. There was an issue that was in denial of service attack, or all the internet protocol fragment rewrites. They read beyond the bound of the packet and called it denial of service. But for a long time, there's been these issues. They call them denial of service attacks, or they're not even known. And it's one of the strange things about read beyond bounds is if you read too much information and you copy it, you don't know about it. Because it doesn't trigger an exception. And we're usually thinking about exceptions or failures in applications. Things like business logic, all these things we can't detect through automation. We can't detect through normal QA. So in this case, I call it a compartment chain. We have a parent block, and you have child blocks, information below that in a binary protocol or file format. And you unravel that or de-encapsulate, if you will, to get those pieces out. And what's accomplished is by link fields. That tells you how much information to get. The thing is, applications trust these. Now, the developers build applications around saying, oh, well, we don't trust these. We're not going to copy too much into our application. We don't want to corrupt that. But it doesn't matter how much you copy, where you're copying from. So these issues are everywhere. Now, RPC, SMB, think of all the protocols that are binary that you guys know about, all the file formats. And then in this case alone, out of my audit, there's 2 dozen that I found identified. It's not particular to Flash because Flash is a bad product. Flash is like any other product that's unmanaged. Anyone using C or C++ is going to have these issues as well. So I'm pointing a finger at the Flash developers at all. So moving on. So here's an example. The first instruction for the audit is that action concept pull. We talked about a string table, like L for P in their file format, where you have strings that you utilize, you're passing on later. So when I supply more strings than that are there, it'll simply read beyond the edges of the pool and add each string. But eventually, it'll read into the adjacent heap and start adding strings, whatever's there, into my concept pool. So yeah, it's just named Goodbye World. Yeah, change course here. So here's the example of the memory layout. I'll show you as well. It's the same action record layout I talked about earlier with the instructions. They're inside the do action layer. So the heap in Windows, for example, you have a series of heaps that are organized. You have what are called the process heap. It's when the process starts, it creates its own heap. You have CRT, like Visual Studio, when you compile code Visual Studio, like Flash or other technologies. Uses a similar heap. And then you have also private heaps you can create using heap create. And these images I've shown, these are actually images representing the heaps that I've looked at for the densities, showing like the black are blocks that aren't allocated, the green are blocks that are allocated. And you also have a concept of heap buckets. So on Microsoft Windows, for example, you have what's called the fronted allocator to allocate buckets of different sizes. 128, 256, 512, common sizes. Then you have look-aside lists for sizes that are frequently accessed and sizes that aren't common. Based on the size of my Swift movie, I can place it across these different buckets, which allows me to read different portions of the heap based on the size of that movie. If you guys follow. It'll be automatically placed by the memory management system into those areas. The goal here is to traverse the heap and read as much as I can through my testing. So for example, 512, I'll go here, 1024. This is completely inaccurate, by the way. It's just for visual representation. So, leading into the proof of concept, string constants are defined and assigned character IDs. So when I do my constant pull explanation before the exploit, and I grab these strings out of the process heap from Firefox or IE or Chrome or any other browser, these are going to be stored inside the player itself in a table. Now the trick is bringing these out. And, there's also a white paper that accompanies this presentation, which you guys can see if you grab it online. It talks more about the concept of read beyond bounds. It's that storage and retrieval are two key factors. Is you store the information and then you retrieve it later. That's what makes the read beyond bounds harder to exploit. Because those of you that have written fuzzers and file injection in the crowd, you have like fuzz file formats. You've seen these. They're in GIF, JPEG, all the major file formats, or especially formats that they're considered hardened. All you hit a boundary and you ignore it. You throw it in a bucket. You don't care about it. But that information is being stored. You found an issue where you can grab information arbitrarily out of the heap and store it. So if you can retrieve it, that's a challenge. So the thing about the rich content, the purpose of this presentation is these file formats allow you a lot more control. Because they have built-in languages, they have compiled code, things that allow you to interact with the stored information, which changes the whole scheme of how you're doing your testing and your auditing. So finally, so I use create text in the following exploit, the text field, for example. So I grab all this input and I'll write it we'll talk more about this. So here's the pseudocode. This I more or less actually wrote in bytecode, more like assembly or shell code. Think about like Flash shell code in a sense, in records. To go out and grab all these strings out, concatenate them together, build them into one block, and then write them to the UI. Now, what makes this a challenge is that the string table is the top of the file. And for this particular bug that I exploited, the constant tags are the top as well. So, and also, when you reference a constant pull ID, there's no way you can do a loop to reference that. What I mean about that is you have to hard code each one. So I'm up here trying to read information down on the bottom, but every time I add one more string that I want to look at, I'm extending that, and I'm just reading these instructions. I'm just reading garbage, my own code. So the Flash player allows jumps to jump outside of tag sections. So just like shellcode, I jump. The old way of doing shellcode, the jump call. I jump to the bottom, then do my do action constant pull, and that right at the bottom of the Swift movie, and it reads data from then on out. Then I jump back. Okay. So read beyond bounds to finalize. The malicious Swift movies that I'll deliver to the application are of different sizes, different kilobytes or bytes to get in different buckets in the heap. The idea is that I want to traverse the heap like heap grooming. There was a talk the last couple of years. Alex Sidoroff did talk about heap feng shui. They really go into this a little bit more. Heap grooming's been around for a while. It's an idea that your heap's like a hard drive. Okay. If you allocate enough blocks, you defragment it, and you can place yourself in a certain place. Like, say for imagine I ended up opening an iframe to my bank. That iframe is going to be 512 byte C++ object. Okay, by doing that, I know that if I defragment 512 bytes for 100 megabytes, I'll defrag it and I can place it right after me. Okay, right after I do my allocation for my Swift movie. You can control the heap in that way across any operating system. I won't say any because there's probably some that you can do a little bit trickier, but that's the idea. You can defragment it. Okay, so demo number 2. So we're going to run the exploit now. Okay. For some reason, this is a... Okay. Can you guys see the whole screen there? No, you can't. Okay. Let's try this one more time. Ah, the demo gods always get you every time, huh? Well, ideally, you see the whole screen here. Let me reduce this just so I can show you guys. Sorry, you guys. I'll give you guys the whole full screen, but not today. Yeah, I got apparently 800 by 600 over here. So each one of these blocks here is increasing in block size. So this first one is 128 bytes, and you move on, and they get bigger and bigger. And the data we gather is based on the process heap around us. So in this example, let's see if we got anything good. Just kind of ran this. Ah, there we go. So those of you in web technologies and browser security know that when you get that browsers create random directory names for cache files. The reason being is that if you can reference those, and you can get content into those directories and reference those and get local access to the system potentially. Because there's a zoning issue called same origin. The idea is you should never be able to read content from a different destination. So I guess that's kind of the premise of this talk as well, is that you have all these competing technologies, complex technologies, built into a browser where information needs to be separated and segregated, but it's not. It's not segregated properly at all. There's a policy enforced, and that policy is enforced pretty well by most browsers. When you get to programming issues like these, for example, these kind of things can be retrieved. So this, for example, if I take this value, this is an asset cache, for example, for Flash. Through testing, we also got the temporary IE cache, all these values as well. We can grab this, put content in the directory, and render content from that, obviously. So this goes into this whole issue of I think like as a remediation we'll talk about later, about segregating address spaces more, which some browsers are moving more towards this, about having like different controls, working in different regions, operating their own data. So, but through this, like you also get, I mean, obviously, like the name of the system, like the user is consultant. You get email addresses. I mean, if I was logged onto a bank or Gmail or anywhere else, potentially any information that's in an adjacent memory, so Flash, you can potentially compromise this. So you can create a little Flash movie that'll run up there, or not. I mean, just saying just Flash, potentially Java, Silverlight, any else that may be vulnerable to this. Silverlight's a little bit different because it's managed good, but issues that are unmanaged, you potentially siphon information out and fire it off to a remote destination. But it's not just Flash that's affected. So I'm trying to point a finger at Adobe saying that Flash is bad. This is a problem with unmanaged code, C and C++. All right, demos are over. So proof of concept statistics. Here's what's interesting about reading beyond the boundaries of memory and capturing data. It's highly reliable. You're just reading. You have to worry about shellcode, addresses, alignment, all these things you normally worry about when you exploit a system. That all you're doing is reading information. You can read that off, and you can analyze it, catalog it offline all you want to get whatever you need. Due to the nature of it, the heap is usually contiguous. Sometimes you'll hit a boundary, depending on how many strings you read, and then it'll fail. That's rare. I mean, if you go and get like the example that I created, I only go out and get 1,000 strings out of 65K, and that gathers together to everything that I want to get if I were to compromise the system. Yeah, and this affects Linux, Windows, Macintosh. We've tested on Linux, tested on Unix, tested on different players. So, because of the high deployment of a Flash player, it affects quite a lot of systems for this issue. Also, because it just simply reads, I have to read different shellcodes or addressing schemes. It's just built in the bytecodes. Common misconceptions. So, I think probably not a lot of people here believe this, but in general, I think people feel that file formats are hardened because they're so popular. In this crowd, obviously, we know that's not true because half of us have been installing patches for the last 2 years every other week for every file format we have in our system. So that's a little bit different. Compiler and OS security enhancements prevent the exploitation of major or the majority of newly discovered vulnerabilities. And I think this is a misconception. I think Mark Dowd, Alex Soderov, some of our other peers here have talked more about this. Is that these ideas like where you check the heap or you check stack cookies, there's still so many ways around these things. And that there's still real issues. Now, to be fair, it does stop a good chunk of the problem. And for Microsoft to introduce these, and the flags like the GCC flags for security as well, stopped a lot of these issues for canaries and vice versa, but they still don't stop all the issues. People understand there's other attack classes and other things out there that can still violate and get an application. If I've mentioned already before, I'll mention again. These issues were found last year. We work with Adobe to patch all these issues described in this presentation. So we highly recommend upgrade to Flash 10. You guys have probably got a little auto-update pop-up box. Click OK, install them. These are all fixed. The code is more stable. There's been a bunch of big changes, and there's also more features for those of you that like Flash. I think Flash is a great technology, and I recommend you guys upgrade to Flash 10 for sure. Closing comments. So for those of you that want to test your own technology, so to help kind of mitigate some of these issues, there's some tools you can utilize. Things like page heaps, for example. So what page heaps does is whenever you allocate memory, you allocate a section like a block. At the end, it'll create a page no access, basically an empty page. And whenever you go to read beyond the bounds of your heap or write beyond the bounds or anything else, it'll throw an exception. You can detect that. So integrate this into your QA process. If you're doing fuzz testing, fault injection, just user monitoring, whatever you're doing, integrate this at some part into the portion of your QA. So you guys can utilize this. Also, train auditors and talk to the auditors, people that come in and audit your software, or if it's internal, external, or vice versa. Have them come in and look for things, not just reading, not just writing. Because being a consultant, looking at software my whole life, I've always looked for things. I focus on like loops where I'm writing. I want to find like heap overflows, those kind of things. But reading is a new thing. Now I think to myself, reading is also can be an issue. Like, can I read too much information? Especially when it's publicly exposed. You have a service or software or a server or a browser, especially web technologies. And finally, those I always recommend, if possible, managed languages. If they're in your bar code, use those. Managed are much safer, better technologies. You don't have to worry about all these issues. You still have business logic and some of the issues you got to deal with. But unmanaged, but just by choosing unmanaged, you run the risk. If speed's not an option and you need speed and you have to go for unmanaged, then go for it. But if at all possible, if you use managed languages, save you a lot of headache in the end. I'd like to thank Josh Salonis for writing the binary template for this. It's a great addition. It helped a lot with the research. And time for questions. Anybody have any questions at all?
So basically, you fuzz the parameters of different streams.
Yeah, the idea is you do tricking in, like you're taking the Swift movies, right? You load them in, and like you're injecting faults in like the byte streams, and you load them into a play or actually a COM object that I use sometimes. I load into a COM object, and then run it, have it parse that out, and take faults from that. Yeah. Any other questions at all, or?
So what kind of things trigger your stop in your buzzer?
Well, it's different events, and this is where it comes like when I talk about fault injection for reverse engineers, for example. You have to detect events, things like you have failures and completion events. So then in the case of Flash, the completion event that I use is the create window call. Then when the Flash player will call to paint the Flash movie on the screen, that's my completion event. So you have to choose that. It's based on like, for example, maybe make it like a close call, like an end read, whatever you choose for yourself to close that read off, to close that, whatever process that, the data is finished.
With your reporting, what sort of, like when you find a fault, what sort of reporting does it do?
Yeah, so it dumps like a context, CPU context, like all the registers information, a call stack. It'll grab data for each one of the registers, like 1 kilobyte, display that. And then also the postmortem analysis will try and like give like a little simple verbiage to describe the issue, like null pointer here occurs this, or like potential stack overflow here, kind of thing. The idea is to create a report that's usable for vendors, right, for testing. This is the first technology we've tested. There's also others that are ongoing right now. We're also testing. Any other questions? Yeah, I think it is a very confusing issue too as well. I think because the idea of just being able to read memory initially, like, and I got a numerous grief from this. The partners, the company I work at, they're like, "What are you guys doing? You just grabbing a couple of bytes?" But ideally, like, talking with my colleagues and the guys I work with as well, is that it depends. For browsers, it changes. Maybe a basic application, it may be different, but browsers you have sensitive information. So if you can read a session ID, like in web technologies, then someone can acquire that and log in as you to your eBay, your Amazon, your other whatever site you're logged into, your Gmail. They can log into those sites, or if it's a credit card number, whatever else, because browsers contain a wealth of information.
Is your mom?
Does that answer your question at all, or? Yeah, no problem. Thank you. Any other questions? Yeah. so typically like fuzzing or fault injection, rather, there's two ways to go about it, obviously. You have generation and mutation. Generation is creating the input itself, like writing the whole file out to disk and loading it to the COM object or the browser. And you have mutation, where you take existing input, which has already had the structure filled out, and you augment that and pass on. So the testing that I do is mutation-based. And you choose generation versus mutation based on the complexity of your technology. Like complex file formats, like binary structures, usually mutation's better. ASCII protocols are easy, obviously. You just insert some string, change it around. Yeah, so for mine, I use mutation-based. No. Well, so the original idea, like, the idea is to make it as close as possible to a real product in real simulation, with that, but at the same time gain as much advantage as you can, right? So, I mean, for example, I can do all in memory and I can fuzz functions, but in reality, those of you that develop software know that I can go fuzz a function all day, but I can't prove that I can get to that input, right? I can go fuzz various functions, but I can't prove I can get to it. So I want to create an atmosphere where I'm testing this as real as possible. So when I know I find an issue, it's a viable issue. I can go to the vendor and give them that issue and say, hey, here's an issue. They can look at it, they can pass over to QA, they can test it, it's viable. Any other questions? Oh, Sweetscape. Sweetscape.com, I believe, yeah. Fantastic tool. Yeah, Sweetscape.com. The template for this is available. There's some for Java, zip, archives, GIF, all image formats. So if you're looking at malware or anything else and you want to see what's going on inside, it's a great tool. Anybody else? All right, well, thank you very much for attending. We appreciate it.